In the previous video, I gave a brief and non-rigorous overview of some algebraic structures, of which group theory is one of them that kind of falls into the middle of how structured it is. And so in this one, I'm going to sort of focus in on group theory, which will be the main topic of discussion in this playlist of videos. And so, as I said in the last video, the properties of a group are these four things here. So one has to have a binary operation, such as addition in mathematics, which is often how we think about it, which gives back another element of the group, which means that it's a closed operation. It possesses the associative property, and so if you're doing if you're doing your operation two different times on three different things, it doesn't matter what sort of order you do it in. So you have your A, your B, and your C, and you're doing your operation like this. It's the same as if you did it like this. So the order of these letters are, of the objects you're performing your operation on does matter, but sort of the order of which you actually do the operation on this particular permutation doesn't matter. So that's the associative property. So it also contains an identity element, E, such that when you perform the operation on an element of your group with the identity, it just gives you the element of your group back. And so for every element R, it also contains this inverse, which when you perform the binary operation on both of those together, it gives you back the identity element. So, addition of integers is often one that's used as an example because it's a fairly simple one where you have your identity element, so E is equal to 0. You have your inverses, which are just the negative numbers, then your elements, which are the positive numbers, such that if you do n plus minus n, whatever number n happens to be, it gives you 0, and if you do n plus 0, it just gives you your number back. So for instance, if you did like 5 plus 0, it just gives you 5 back. If you do 5 plus negative 5, it gives you 0. And so this is a very common and easy to understand sort of group here. But I put this little illustration over here just to show that it doesn't have to be numbers that you're working with. And so what we have here, so we have these circles here of different colors in this particular order, and a group operation here would just be switching two circles with each other. So when I go from this one down to this one, I'm just switching the red and blue here, and the inverse would just be doing it backwards, so getting it backwards. The identity would just be sort of not switching anything, but you can see, so you can switch the red and blue, then you could do another one where you switch the red and green here. You can do another one where you switch the red and blue here, and then you get back up to here by, this one and this one are actually the same. What I wanted to show is that you can do this in 3 steps here, but it also can be done in 1 step, and that's that closure thing I was talking about, where you always get back an element of your group no matter how many times you sort of do the operation, because it's closed, and so every operation gives you another element of the group. And so you can sort of boil things down to just a few simple operations. But I'll get into that more in the future. So that is sort of the properties of groups, and like I said, this is just to show that a group doesn't necessarily have to be numbers, even though that's sort of a nice, easy one to think about. So one other thing I wanted to point out before moving on is in group theory, you often see the group operation as just being putting your two elements together like this, which would then give you something C. And so this is one of those things where in group theory, you end up using things that mean something else in other situations. Where when you take like a just an algebra class, usually when you put two things together like this is a multiplication. But what you'll find in group theory is that this sort of putting things together is used for pretty much any binary operation. So if we're using addition as our binary operation, then A, B together would be our A plus B. And so that can kind of get confusing sometimes with this, and like we'll see in future videos, I'll be using, and oftentimes for groups we use capital letters for the group, and lowercase letters for sort of the elements of the group. But it's the same thing though, where just putting it together sort of side by side like this is just performing the group operation, though oftentimes I will probably sort of explicitly show it like this. And then of course if you get into higher structures where you have both an addition and a multiplication, then like in vectors and things like that, you'll see it with the pluses being sort of explicitly used. But for a lot of times in group theory, as I said, just kind of a warning, you'll see this right here being done for the group operation, regardless of what the group operation is. But anyway, to move on, so the next thing I want to talk about is this uniqueness of combination. And so what that means is that if we have the following two conditions where we have A plus B equals C and A plus D equals C, so A and C are the same here, then B has to be equal to D. You can't combine A with two different things to get C. So if you have two different things here, they have to just be the same thing. And so there's this uniqueness of combination. And sort of conversely, when you do A plus B, it will always equal C. You can't do A plus B and then get C one time, and then A plus B and then get D another time. And that's if you do this in the same order. So we're assuming non-commutativity here. So it might be the case that if you instead did B plus A, then you could get D. But if you do it in this same order, then you will always get C from that. So in other words, taking A and B with the group operation plus will always yield C. And so kind of a specific instance down here. So for example, say we have 1 plus B equals 5 and 1 plus D equals 5. And so 1 equals 5 minus B and 1 equals 5 minus D. It has to be the case that B equals D equals 4. And so that's sort of the uniqueness of combination there. So some symbols that will get used, and this is actually getting into sort of symmetry operations, and I will show more in the next couple videos how symmetry operations are a group. And so a symmetry operation has an identity element, which is just doing it's doing nothing to your object, and so you just get back the same object. We have Cn, and so that is a rotation. So when you see C with some number in the subscript like that, that means a rotation, and the number is the number of rotations you have to do in order to get back to the identity element. And so it will be 360 divided by theta, where theta are the degrees of a symmetrical rotation. N is therefore the number of times the object has to be rotated. For instance, a square is n equals 360 degrees divided by 90, so it would be C sub 4 like this. And a rhombus, which we see down here, is 360 divided by 180, so it's 2. So we have C2 here. And so we see that this that we have A up here and C down here. We do a 180 with it. We have our C up here, or A down here, and the D and B also switch sides, and we do it again, and we just get back to where we were. And so that's why it's the C sub 2. And then so for the square we have down here, so you have to do 1, 2, 3, 4 rotations in order to get it back to where it was at the beginning. So we can follow this little O around here for each 90-degree turn. And so that these C with the subscript are rotations. E is the identity element, which is just doing nothing to your object. So then this sigma, the Greek letter sigma with a sub or superscript rather of a number. I think most people, but I will be putting in parentheses because we will be using exponents here, and so we want to distinguish this number here from an exponent. But because these numbers here are just distinguishing the different reflections that we can do. And so, for instance, if we had just a sigma 1, that would be something like this. So this butterfly, you can reflect it once. There's one axis or plane of reflection, where a square has three different ways you can reflect it. So it would have a sigma 1, it has a sigma 2, and it has a sigma 3. And in fact, if you do it in 3 dimensions, it actually has another one, which is a plane that's I guess parallel with the screen. And so sort of the top of the square would be sort of reflected so that it's now inside the screen or facing into the screen. And so that's actually another reflection that you could do with that. And so reflections, as I said, are symbolized with the sigma, and so this n in parentheses, or the numbers in parentheses up there, are just telling you sort of which reflection you're talking about. So I put here the square has sigma 1, 2, and 3, but as I said, you could think about one that's sort of just changing the face of the square from facing out of the screen to facing into the screen. Then there is an inversion here, which we see is something in 3 dimensions, where we take this 1 and the 6, those trade places, the 2 and 4 trade places, and the 3 and 5 here trade places. So all of them trade places all at once. So it's like each one of these spokes, or I guess chemical bonds on here is how you would use it in chemistry, are sort of all getting pulled in at the same time here, and sort of moving in and then sort of moving back out on the other side. So the whole thing is being inverted, and so that is denoted with just a lowercase I. Then there is this improper axis of symmetry, which is essentially just a rotation plus a reflection. And so I just took this picture with my phone out of my physical chemistry book, and so we see that this S2 here is a combination of C2 and sigma here, and so what we're doing is we're rotating around this axis. So this little curl part here ends up over here. This one facing down ends up over here, and then we sort of reflect through this plane right here, so that this one kind of gets pulled down there, and this part gets pulled up there, and so that is an S2. So this scroll here. So note that although the scroll has S2 symmetry element, neither C2 axis nor the sigma plane, as indicated, are by themselves symmetry elements of the object. And so you can't, well, if you just did this all the way around, that would just be the identity element, because you don't get sort of the same thing again by doing that 180 degree turn, because this thing doesn't look like this thing. And same if you did the reflection on this thing right here, where this gets reflected down, this gets reflected up, would not give you the same thing. And so you have to do both the rotation and the reflection. And so that's why it gets sort of its own sort of symmetry designation. Because as we'll see in the next couple videos, you can sort of reduce symmetries down to a single symmetry operation. So if you do multiple symmetry operations, you can always reduce it down to a single one. But these S ones cannot be reduced down to a single one. And so this is actually a symmetry group that I'm going to be using as my example quite often in these videos. So the symmetry group is called the C3V. So that is sort of the name of this entire symmetry group here. And I'll get into naming of these in a later video, but for now we can just look at the symmetry operations. So this is our object here, and I have each corner numbered, and I have this little plus here so we can sort of see what happens during a few different reflections. So we can do the identity to it, which is just doing nothing, so we just get the same thing. So the C3 is a rotation, and this would actually be a rotation of 120 degrees, and we see it's 3 because we'd have to do it once, twice, 3 times to get back to where we were. And then we have the C3 with the bar over it. That's sort of the inverse of that, and once again you have to do that 3 different times in order to get back to where you were. Then we have these sigma elements here, and we see that this plus right here is being switched over to that side when we do this sigma 1. The 2 and the 3 are switching sides, and we can see that the sigma 1 is its own inverse here, because if we just did this again we would get back to where we were here. And then we can do a reflection along this plane here, or a reflection along this plane here. And as you can see in this one, we're not considering that sort of plane parallel to the screen symmetry, so we're just counting this as a 2-dimensional symmetry. So 3-dimensional symmetries are also a thing, and those are very important in chemistry, but for now it's just kind of our example symmetry group here. I will be using this C3V, and so this works on an equilateral triangle, but as we'll see, these symmetry operations can be done on other things as well. And so that's why the actual symmetry operations themselves are being used as the group. And so I'll show in the next video how we can sort of get like the identity elements and how the inverses work, and how we can sort of use a whole string of these symmetry operations, and then just sort of reduce that down to a single symmetry operation, because every sort of combination of symmetry operations just gives us another symmetry operation. That's why it's a closed group, and so that is why symmetries are, one of the big things that group theory is actually used for. That's why this symmetry group here, this C3V, is going to be one that I use as an example. So we can see that if we were using instead like a square, this would actually be a C4 group, and so it would also have its own axes of reflection here, and so this would actually have a different symmetry group. But like I said, I'm going to be talking it sort of with generalities a lot, but then I want to try and tie things together using this C3V particular symmetry group in order to make things more concrete for you. But anyway, I think that was everything I wanted to talk about in this video. So I think kind of the takeaway from this are these properties of the group, that we have this uniqueness of combination, that groups, as I said, don't have to be just with sort of numbers. And in fact, as I said, quite often they're not with numbers. These symmetry groups are probably one of the most important parts of group theory, and that's why it's going to be the ones I use a lot. And because the sort of motivation or impetus behind making this video series is to apply it to things like physics and chemistry and things like that, and that's where these symmetry groups come into play here. And so that is going to be how I often talk about groups in terms of these symmetry operations. I guess I should also point out that there is another type of symmetry which would work on something like a circle, which is a continuous symmetry, where you can see this has, pretty much an infinite number of axes here of reflection, so you can rotate it. You have your circle, and you can rotate it by sort of infinitesimal amounts, sort of an infinite number of times. So those get into things like Lie groups and stuff like that, which I will probably talk about quite far down the line. But for now, I'm going to be using these sort of discrete symmetry groups. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.